What's up, everybody? Welcome back. We're going to old school today, back to pencil and paper. When we first started learning about definite integrals, we related it to areas of a graph, and specifically we said that a definite integral was net area in between our curve and the x-axis. Today, when we start chapter 7 and we're skipping 7.1 and going straight on to 7.2, lots of times it's really interesting to know what the area in between two different curves are instead of just the area between a curve and the x-axis. And so let's start with a little bit of a definition here. And what this says on the paper here is that if we have two different functions f and g that are continuous functions, and the key to this is if we know that one of the functions is up above the other one the entire time, so larger than, in this case f, throughout our entire interval, then it's really easy to calculate the area in between those two curves. It's just a definite integral from a to b, and then we just take our two functions, the one on top, the larger one first, minus the lower one. And just to give a quick visual representation then, if we have something here from, let's say this is a to b, let's say we have an f of x here, and then let's say here's our g of x. Clearly this fits our definition. The f of x is larger than the g of x the entire time. If we just do this definite integral here, that would calculate all of this area right here. And as you explore it, it should make sense, right? Because if we had just done the integral of f of x, that would give us the area from f of x all the way down to the x-axis. And then if we do a separate definite integral of g of x, that would take all of this area down here, and then this shaded, what I've shaded here, would be the f of x minus that lower one. Lots of times we can visualize it really well for something like that. We have more trouble all of a sudden if we have an f of x that looks like this and a g of x here. And let's again say that this is a to b. It still shouldn't matter as long as it fits our definition of f of x being larger than g of x the entire time, greater than or equal to, that is. This should work. So once again, to find this area here, it would be nothing more than this definite integral from a to b of the f of x minus g of x. So let's put that into practice. We'll do two examples today. What I'm calling example 1 you can already see listed here. It says find the area between y equals 2 and y equals sine of x from x equals 0 to x equals 2 pi. I am okay, you guys, in this section with you using our calculators to help speed things along, including to graph it. I don't think we need help with the graph of this one though, because one of them is just a line and the other one's sine of x, which you guys are really familiar with. So let's draw, I'm just going to do this faster without the calculator. Sine of x would be this, where I know that this is a 1 and this down here is a negative 1, and then y equals 2 would be up here at 2. And we're asked to find the area in between those two things, so that would be the only question you need to ask yourself. And really for what I'm calling day 1, it should be true all the time. One function should be larger than the other the entire time. In this case it absolutely is. So all there is to it, the only work once we look at the graph of this, we just need to do then a definite integral. We were asked to go from 0 to 2 pi. The formula says take the upper function, in our case is a 2, subtract out the lower one, which is a sine of x. Get our notation right, we're using x's, so this should be a dx here. So this is the key to our problem. We just need to calculate this definite integral, and that'll be the answer to our problem. And as I mentioned, I'm okay with you using your calculators in this section. Technically, keep in the back of your minds, this could show up on non-calculator. This is something that you know how to do antiderivatives for, so we should be able to find definite integrals for it without our calculator. But just to speed things along, we'll use this. What I like to do, since we're going to do several of these in the homework, I go ahead and in the y equals store in y1 usually the upper function, sine of x, I guess I should check my mode, make sure I'm in radian mode. I am. By storing those in y1 and y2, then every single time when I go to use math 9, the fn int, well, I'm just going to type in that I want to do y variables y1 minus the lower function, which I stored in y2. Remember, it's with my operating system, it's comma x, comma lower limit, comma upper limit, which is 2 pi. So in terms of calculator use, we've said before that it's okay, is you don't want to write fn int on your paper, you want to use our good math calculus notation here, which is what I've done. So you can skip right from this to an answer. I'm okay showing that it's an approximate rounded to 3 decimals. I think we could get a little fancier here. I'm guessing, since this involves sine, that there's probably a pi involved with our answer, and usually we're multiplying by pi. So to see if it's something nice, I want to do the opposite. I'm just going to divide by pi and see if that answer is something even nicer. Sure enough, it was exactly 4. So I think rather than giving this answer, if we can figure that out, it'd be a little nicer to just give our answer as 4 pi. And 4 pi is approximately 12.566. And that's the exact answer we would have gotten if we had done this by hand. Okay, so that's example 1. That's all there is to it. Let's slide this paper up. Let's do what I'm calling example 2. As we usually do, we add a bit of a complication here. The thing you'll notice that's missing in the last problem, I told you specifically we were going from 0 to 2 pi. This one doesn't say that. It just says we have an area enclosed in between 2 different curves. And here it looks like we have a parabola opening up, parabola opening down. Again, I could graph it by hand, but I think this time maybe I'll just real quick take a look to see what this looks like. So I'm going to store, I'm guessing the parabola opening down is the upper one, so I stored that in y1. And let's look at x squared minus 4. Just do a standard window here. See if we can see anything good here. There's a parabola opening down, the first one. Sure enough, the parabola opening up. So, sorry if you couldn't see that. Here it is a little better, so they're parabola opening down and then up. So what we're really looking for is this area in here. If we're going to turn this into a calculator problem, remember what the requirement is we're going to want to do a definite integral excuse me, from here to here. Well, the calculator ready step for that is we want to show that we're going to set the two functions equal to each other. So I'm going to show that I'm going to take x squared minus 4, set it equal to 8 minus 2x squared. This is something that we could solve by hand, but let's do second calc and find the intersect, since we're saying it's calculate active. First curve, it's on one of them, that's good. Automatically switch to the other, so I'm going to hit enter again. It's going to ask to guess. I'm just going to go somewhere close to one of them. Looks like we get x equals 2. I'm going to repeat that real quick. First curve, second curve. This time I want to guess over. I'm just going to type in, I'm going to guess near negative 2. And sure enough, it told me that the intersect. Okay, so in terms of work, show that you're setting these two equal to each other. Get our answer. That tells us that to find our area, we just need a definite integral from negative 2 to 2. This area that's enclosed by these two, during this time, one function is above the other one the entire time, so that fits our definition from the beginning of the video. That means we can just take our upper function. Our upper function's the one that's the parabola opening down. So that's this one. So I'm going to take 8 minus 2x squared. I'm going to subtract out the lower function, since that's what our formula said. Get our notation right. We're using x's, so I need a dx there. Here's where a majority of the points are, is everything I have written already. And then what I really just need to do, make sure, I have the upper function in y1, the lower one's in y2. So if I go to the home screen, I had it set up perfect. If I hit second enter, the copy and paste command, I get back to fn int upper function minus lower function from x. I do need to fix my limits. I want to go from negative to positive 2. Hit enter, it does some thinking, and we get an answer of 32. Of course, we could have done this by hand. Historically, most of the time on the AP, this is on the calculator section, so we can use the exact technique I've been showing. Maybe every once in a while we'll practice by hand, because it's not a definite thing that'll be on the calculator section. Alright, that's it for day 1. You'll get some practice with these ones where you'll always have one function above the other, and then we'll mix it up a little bit. We'll have 2 more days of this where we'll add a little bit of complication in. Alright, that's it for this one. Hope you guys enjoyed the video. I'll see you all soon. Bye-bye.